time for today's LeetCode problem. So continue with 2 pointers. This is an easy problem. Hopefully we can get it done within 20 minutes. Let's see. Oh, it's not loading. Okay, let's start the timer. It's subsequence. If S is a subsequence of T, so does that mean substring? Oh, I see, okay. Subsequence. So it does not have to be a substring. We can just take some letters from it as long as the order is reserved. That is a subsequence. Interesting. A, B, C true. A, X, C not true. Okay, only lowercase English letters. We have a follow-up, but let's do this first. Subsequence. Okay, first idea is we simply traverse T, and each time we see a letter in S that we need, we then okay, so 2 pointers, one pointing in S, one pointing in T. So the pointer is gonna go until we get the first letter in S, and then we move the pointer one step forward, and then we continue to move this pointer until we get the second letter. And if we have moved to the end, we haven't moved to the end for S, then we do not have that subsequence. Okay, let's write that. We can call it I or J, or pointer 1, pointer B, I guess. Let's start with 0 while J is smaller than the length of, well, J is always gonna go forward, so we could do for J, no, we don't need that. For J in range, that's gonna go from 0 to length of T minus 1. So J is gonna traverse the string T. If Si is Tj, then we move S and J will also be moved. If Si is not Tj, then nothing happens. We simply move T forward. And then when we have done this, we want to return whether I is equal to the length of S. Okay, that's what I'm thinking. Index out of range. Oh, I see. Okay, we could do, okay, the 2 ways to fix this. We could do if I is equal to length of S, then we just return true. Otherwise, we return false. Or we could add the extra condition there. Still out of range. Oh. Wait, so last case, if I had gone to the last one, then that would give index of the range. Okay, so now we just going empty string. Empty string. Okay, so we still need this. But if it's empty, is that true or false? Oh, false. Okay, what's wrong with this? So I, j both 0. Length of s is 3. A, yes. I is now 1. J is 1. Nothing happens in this loop. And then B, J is 2. I is still 1. So that will be the same. I is now 2. Okay, so I is 2. That's not the same, not the same. Now I is 2. Oh, I see. I is 2. J is 5. They are the same. I plus. We still need to do it like this. If I okay, now we have it. Okay, it's efficient, time and space wise. Alright, so this works. So this fixed the index out of range problem, because once we reach the last element in the string s, it will still increment 1, and the next round, if t hasn't reached the end, then that would give index out of range here, because I is not length of s. And if we have reached the end of s, so we have already reversed this, then we don't really need to look anymore. We can actually just return whether we have, well, actually, if once we reach the end, we already know that's going to return true. So we could break, add another line to break there, just to save the rest of t. The rest of the traversal is not necessary anymore. So, okay, well, let's just put it there anyways, because that would actually save some operations. If I is at the length of s, we can just return true. Would it just be false otherwise? Wrong answer. Interesting. Okay, so I guess we keep that. Okay. Well, at least in this case, it did give a little faster runtime. Alright, So there we have a very efficient solution. So time and space, let's see. We are traversing T, so the most work we will do is to simply traverse the entire T, but we could also break early in this case. If we already found all the letters that we need in S, then we don't need to traverse all of T. We can just return true already. So this will be linear, and most likely it will even break before, so this is at most linear. So linear time constant space, because we're not using any extra data structure or anything. Alright, linear time constant space. Let's look at follow-up question. Suppose there are lots of incoming S. Okay, and you want to check one by one to see if T has its subsequence. So T is still the same, but we have lots of incoming S that are changing, and we want to continuously check if S is a subsequence. So T doesn't change, S changes all the time. Is there any way we could have a more efficient algorithm? I can't seem to think of anything. So right now we are traversing T for each incoming S, which is redundant because we have the same T, so in theory we shouldn't need to do the same traversal every single time. But the S is gonna be different every time. I can't actually think of any solution that's different. Oh, dynamic programming. So we are using 2 pointers. We are not using dynamic programming. Okay, I will think for 2 minutes. If I can't think of anything, let's just have a look at top solutions. wait. Now I'm actually unsure what this means. Okay, suppose there are lots of incoming S, and you want to check one by one to see if T has its subsequence. So does that mean if T has S's subsequence, does that mean we want to check if T is a subsequence of these incoming S's? That would be what it means from this sentence, but this will be the opposite of this entire example because we are doing S is a subsequence of T. T is the longer one, and now this sentence would be T is a subsequence of S. Well, I'm not sure what it means. Alright, let's have a look. What can we do? Okay. So this is the same algorithm, but only this part, it did not, well, this is fine because this is extra part to increase efficiency, but it did not need to check this. Why does it not need to check that? Because that will give us index out of range error. Oh, I see. What if S is actually longer than T? Then it's false right away. And if S is empty, then that's true. Otherwise, it's doing the same thing. Okay. So it didn't mention anything about the follow-up. Yeah, so that handles the index out of range problem. Okay. Okay, let's have another look. Okay. Dynamic programming. I do want to see a dynamic programming solution. Okay, brute force. Recursive, alright. Recursive. Okay. Let's see, this would be check whether the size of the longest common subsequence is equal to the size of string 1. The size of the longest common subsequence. Okay. So A needs to get the longest common subsequence. Not very clear what this algorithm is doing though. A subsequence. Alright, let's look at this follow-up. Binary search. Tree set. Follow up linear time for pre-processing m log something for each s. Example 1. Okay, interesting. A 17 B 03 C 6. A B C. Oh, I see. Okay, very smart indeed. So we need to find these 3 letters. So let's pre-process this and see where the indices for these letters are. So A is at index 1 and 7, B is at 0 and 3, and C is at index 6. And now it will only work, which means it will only be a subsequence if this ABC comes in an ordered ascending way. So 1 has to be followed by 3 and then 6. So 1 0 doesn't work, and 7 0 or 7 3 doesn't work. Now we have 1 6 and we have 5, which is not ascending, then this doesn't work. Okay, so this will be linear time for pre-processing the string of T to find out the indices for each of these letters that we need to find. And then this part, will that be faster than linear? Oh, interestingly, so it is T that are changing, not S, which means it's subsequence. So So the longer strings, those are the ones changing. S is subsequence. The longer string has a subsequence, that's the shorter string. So the longer strings are changing and the shorter string is the same, which is the same as the example we were just looking at, but this is completely the opposite of this whole question formation. This is exactly the opposite, so that's not good. But anyways, let's go back to that solution. So this pre-processing step is linear, this part, and the next part we are just using this, and we're gonna see if we can find the sequence that's ascending. So what's the time complexity for that? Actually, I'm not sure how to. What would be the time complexity? Actually, I don't know. Let's see if they explain that later. Okay, so a little bit more complicated to write this code. It's using binary search. That's where the log comes from. Binary search. Okay. Binary search. Oh, I see. Okay, very smart, but kinda complicated. We will need to have good understanding of try and also binary search, but this is where the log comes from. This is an easy question, but this could have been much more complicated if we want to use this binary search and try. Let's see the Python code version. I'm curious. Default dict, enumerate, append. Okay, so the dictionaries we are putting all the letters in T in this dictionary. Oh no, we are okay. No, I see. Okay, so C is the character in the string T. So for each character, is the C is the key here, and I, which is the index. I is the index starting from 0. So for each character in the string, the longer string T, we are gonna append its index. So now we know the indices for each letter. And now we want to do this for S and index C. Okay, so for each character in S, previous is currently at 0, so bisect left. We have to know what this does. I have not used that before, so let's see. J is equal to the length of so J, okay, this, okay, I think I actually need more time to look at this. So this is a dictionary, and this starts at 0. And then we're putting here, this is a list of sorted integers. So that's the dictionary. Okay, so dictionary at the first letter. Okay, let's say if S is ABC, then this will be all the indices for A in the string T. Okay. And what this returns is the leftmost index to insert the given element into the sorted list. If J equals length to false. Oh, I see. If this part, let's say, if for character A in T, if the indices were 0 and 3, for instance, and we want to insert 4, or even insert 2, length of that would just be 2. If you want to insert 2, that's false. But we can insert 1. Oh, I see. Then previous is okay. Alright, this is some super smart solution, and I think I need to go over that with a concrete example. So it's already 36 minutes, so I will end the video here. I'll go over this with an example later. If you would like me to actually review this with an example, let me know. Otherwise, I'll just do this for myself and conclude this video. Alright, I will see you in the next problem tomorrow.